Okay, DTrace, Dynamic Tracing in Oracle Solaris, MacOS X and FreeBSD by Brendan Gregg and Jim Morrow, Prentice Hall, 2011. Before we start, book page numbers are at the top right of the screen. No page number means I'm interjecting my own ideas, which may be dangerous since I'm still a DTrace novice. The book is from 2011, and some of the scripts presented no longer work, but because this is a presentation, I can make it seem like they would. Remember, the concepts are more important than the details. And finally, I'm sure there are mistakes. These are mine. DTrace was first released on Solaris 10 in 2005. It was open source the same year. The audience for the book includes people that would want to observe and debug production systems. It will be easier to learn DTrace if you already know C or a language whose syntax is close to it. The book is quite long and can feel like a reference book in places, but its aim is to teach DTrace by going through lots of examples, more like a cookbook, and to provide guidance on how to debug systems. If you want reference material, see the DTrace guide. There are many other excellent resources on DTrace. To point out a few, the book scripts are available from GitHub, and the DTrace guide is available from dtrace.org. Here's the book's table of contents. Part 1 describes what DTrace can do and how to read dscripts. Part 2 covers how to use DTrace. Chapter 3 covers CPU, memory, disk, file systems, and networking. Chapters 4 through 10 go into great detail for specific subsystems and also cover applications and databases. Part 3 covers various topics. If you want to read the book quickly, I would suggest skipping chapters 1 and 2 and go through chapter 3, System View, and then check out Appendix E, User Static Defined Tracing. The book is over 1,000 pages, so I won't be able to go over everything in an hour. So we'll go through the first 3 chapters, and that's still going to take more than an hour. Chapter 1, Introduction. DTrace is easy to learn, but if you don't have a good understanding of how the operating system works, you will be limited in the questions you can ask. In this untested, non-scientific graph, I would say the steps required to learn DTrace to be able to regularly solve problems would be to learn DTrace, learn some probes, look at dscripts, learn system calls, identify and fill gaps in your knowledge, practice, and then you're done. You can solve problems. The book mostly covers these first 3. Chapters 4 through 10, which we're not going to cover in this video, have diagrams that will give you an idea of how the operating system works, but these shouldn't be the only ones you look at. DTrace isn't the first tool to reach for when debugging a problem. You'll instead start with PRStat or TOP or VMstat or some other tool, and after using those tools, you'll have one or more questions that you want answered, and this is where DTrace is invaluable. Think of something you want to measure and write a dscript or one-liner for it. Run the script and answer your question. This will likely lead to another question you want answered. Write a script for that, and so on, and then you find the source of your problem. It's just that easy. It's best to learn DTrace on a system whose source code is available, like FreeBSD or one of the Illumos derivatives. Not having the source code is less than ideal, but it's also available on these systems, MacOS X and Oracle Linux, as well as others. Don't use the Open DTrace port on Linux in production, and DTrace is not available on Windows, but it's not Unix specific and it is open source, so if you're feeling ambitious and have the skill, you could port it there if you wanted to. DTrace has all of these features, but its primary feature is that it's safe to use in production. Right now there are many systems that are mission critical to businesses using DTrace in production to provide metrics and to do monitoring. And when these systems don't behave as expected, DTrace can be used in production to diagnose problems. It's designed to minimize probe effect, and DTrace will stop if it sees it's hurting the system. Also worth highlighting here, Unified Instrumentation allows us to inspect any layer of the software stack with one tool, and related to this, for any question we have, DTrace can help. The limiting factor is our understanding of the OS, not DTrace's capability. On the left, we have the simple model of an operating system. If you didn't know, system calls are the mechanism through which user-land software accesses hardware functionality via the kernel. On the right, we have a short PHP script. This script gets the current directory and creates an iterator for it, and then prints out the list of files and directories inside. So if we were running the script from our home directory, we might see something like this. So think, when we type this command and it executes, what layers of the OS would it go through? Typing commands would start with hardware. The shell is native code, and after pressing enter, we would start PHP after forking a process. Next, we get the current working directory and an iterator for it. It seems like the kernel has a file systems module, so we'll go there. The kernel returns the data we need. PHP continues again, this time printing out the results, which we would see after they go through the network via hardware to our system. Finally, we would see the output. So in an Alfred Korzybski, the map is not the territory sense. This isn't quite right, but it's also not too far off either. So using our current tools, how might we inspect this program as it runs through the various layers of the OS? We might use debuggers, or more likely printf, for dynamic languages and native code. For libraries and system calls, we might use something that can trace system calls like truss or strace. For the kernel, we might use a kernel debugger like MDB. For hardware, we might look at hardware counters via CPU stat or kstat. If only there was an easier way. There is. DTrace certainly doesn't replace all these tools, but for observing a running system, DTrace is the best tool for the job. On the right, we see an overview of the DTrace architecture. For this video, we're primarily interested in two things. First, writing scripts or one-liners in D, and second, the probes to use to instrument what we want to observe. And because probes are grouped by provider, the various providers. Let's start our PHP script. And let's say at this point in the execution, we started a DTrace script to observe PHP functions. When PHP functions execute, a probe fires. When this happens, we can inspect the arguments made available to us by the probe and print something out or count calls. Many arbitrary actions are possible. DTrace is instrumenting the entire system, so if multiple versions of our script were running at the same time, the probe would fire when any of them execute a PHP function. Same thing if different scripts were running. But this diagram has a lot to look at already, and DTrace can certainly instrument a single process, so let's go back to a single script. We'll kill our DTrace script, instrumenting PHP. A good place to start when diagnosing a problem is to look at system calls. Those probes are available via the syscall provider. Start another script, and the probe fires when we do a read. Or we could look at I/O and the file system. Here a probe in the fsinfo provider fires. We probably wouldn't want to do this, but if we wanted, we could look at many different probes from different providers at once. And when PHP calls echo, one of our PHP probes fire. And a syscall probe fires when we call the write system call. And lastly, an I/O provider probe fires when we write to the network. Okay, maybe we're convinced DTrace can help us observe these layers. Where do we start already? Let's look at some scripts. Note we're root. We're looking at one probe. We press enter. DTrace tells us how many probes it matches, and as various processes enter the read system call, the probe prints itself. We press Ctrl+C to stop execution. By default, probes print themselves, but we don't know what application or process is causing the probe to fire. Let's do something more useful. Here we're adding a clause in curly braces. The probe has something to do with processes successfully executing. The clause has one action that prints arguments. Let's start the script. Again, it tells us how many probes it matched. And in a separate shell, or as different users execute processes, the probe prints and the command and the command line arguments are printed. The one-liner is in single quotes. Note default output, same as in the first example, but we also get arguments used to start the processes. One more thing to show, let's guard this clause by adding a predicate. Predicates are conditionals between probes and clauses, which begin with end which begin and end with a slash. This probe fires when we enter the read system call. Remember, DTrace is instrumenting the entire system, so if you wanted, you could instrument DTrace with DTrace. But we probably don't want to do that. With this predicate, the clause executes only when the program performing the read isn't DTrace. Also different in this example is the use of a special variable called an aggregation. This script also takes advantage of the fact that DTrace can see arguments passed to the called function. Here we're using the first argument of the function arg0 and using it to get information from file descriptor variables FDS. We execute the script, DTrace matches our probe arguments with one probe, and while we think the reads that we're interested in observing have happened, we press Ctrl+C, the script stops executing. Note the keys in the aggregation, exec name and path name, print in their own columns, and the values for the keys, in this case count, also prints in its own column. With this example, we start to get an idea of the power and ease and flexibility available to us with DTrace. We've seen the syntax for DTrace basically follows a probe predicate clause pattern. We can inline scripts in single quotes using tacn, which tells DTrace one or more probes follow, or we can save scripts to files, and we could execute them using tacS. The same probe can appear in a script more than once, having different clauses, and we can combine probes using commas. The same predicate clause will be used on all of those probes. To review and clarify some terms, scripts are written in D. Scripts are passed to a program called DTrace that is one of many consumers that use the DTrace framework. In Chapter 3, we'll look at these other consumers as well. Providers group related probes. Most probes instrument specific parts of the system. Predicates allow us to conditionally execute clauses. Clauses contain one or more user-defined actions. There are built-in variables like exec name, and we can define our own variables, like @reads in this example. DTrace has special built-in variables called aggregations, and there are many built-in functions. DTrace tacl lists all the available probes. Each probe has an ID. We use a probe by combining provider, module, function, and name using colons. Providers group related probes. Module is the kernel module where the probe is located. Function is the software function that contains the probe, and name is the meaningful name to describe the probe. To see how many probes the system has, pipe DTrace tacl to WC. OmniOS is a server distribution, and it has over 76,000 probes. MacOS X, it has over 200,000. Note provider is in the second column. Let's get a sense of what providers there are and how many probes they have. Here we see probe counts by provider. We pipe DTrace tacl to sed and remove the header line and only print out the second column, sort the output, and tell Unique to give us counts, which gives us this output. We see most probes are in the FBT provider. Most providers map to hardware, and it's more or less obvious what they're for. Let's look at some less obvious providers. FBT is function boundary tracing. This allows us to instrument the entry and return of nearly every kernel function. These probes are dynamically generated from the kernel, so if we use them in scripts, as the kernel changes, our scripts may need to change. That's why this and some other probes are said to be unstable. MIB stands for Message Information Base. These probes allow us to view Simple Network Management Protocol or SNMP counters. Most probes simply fire, but the profile providers gives us probes that 1. Can profile the system at a user-defined rate, say 997 Hz, and 2. Can execute after a user-defined amount of time, say after 1 second. Last, there's SDT, which stands for Statically Defined Trace Locations. These probes were added to the kernel by kernel engineers for the sole purpose of exposing kernel state and actions to DTrace. Use DTrace tacl, tac_P, and specify a provider to view probes for that provider. Or you can use tacl_P together. Or use DTrace tacln and complete as much or as little of the probe as you want. You must use 3 colons though. Here, only provider has been specified and will list all the probes in the I/O provider. In the second example, provider and module have been specified, but function and name have been left blank. This would list all the probes in the I/O provider that are in the Gen Unix module. When a probe fires on function entry, we can inspect the arguments passed to the function. If we were tracing this function, when we enter the function, the probe would fire and we could inspect arg1 and arg2 here. How do we know what these arguments are? Source code is best. We can also use DTrace tac lvn and then the name of the probe, and on some systems we can see what the arguments are. Here we see TCP input data has 5 arguments. Say we wanted to know more about TCP info. We could use cscope, or we could go to src.illumos.org and enter the symbol that we're interested in the symbol field. Looks like this. Note I've picked Illumos gate on the right. DTrace can also do graphics in the form of ASCII art histograms. The quantize and lquantize functions can be used to achieve this, and also allow us to quickly determine the number of modes in a distribution. So, in the conclusion here for Chapter 1, DTrace is a revolutionary technology that provides observability up and down the entire stack without requiring code modifications through the use of instrumentation points called probes. DTrace providers, a core component of the framework, manage probes and enhance observability by abstracting complex areas of the system with intuitively named probes and probe arguments that facilitate capturing relevant data. The D language and DTrace variables, functions, and subroutines combine to provide a powerful and flexible environment for instrumenting and observing systems. In this chapter, we introduced all aspects of DTrace, architecture, core components, and the D language. Examples demonstrated the use of DTrace probes and some of the available DTrace functions, subroutines, and variables. Throughout the remainder of this book, we will expand on all the material presented in this chapter with an emphasis on DTrace by example. Chapter 2, the D language. D was inspired by C and awk. It has built-in support for variables, strings, and a special data type called an aggregation. We can inline our program using DTrace tac n, or we can put scripts in files and tell DTrace to execute them by using DTrace tac s, or we can add DTrace to the execution path of our script, also include tac s, make the script executable, and you could run the script directly. D scripts basically follow this pattern: probes, predicate, clause. Predicates allow us to conditionally execute clauses. The only valid combinations are the following: one or more probes, probes in a clause, probes, predicate, clause. Probe format. Probes are grouped by providers. New providers are added over time. Module, the kernel module or user segment for the probe. Function is the software function that contains the probe. And finally, the name of the probe. Not every probe has every field defined. For example, syscall read entry does not specify a module. Instead of if statements, DTrace has predicates. When the UID variable equals 101, the clause following it would execute. Writing PID by itself in a predicate is the same thing as writing PID not equal to 0. Predicates can contain Boolean operators. Clauses contain one or more actions or statements, which must end with a semicolon. DTrace ignores whitespace. Statements can manipulate variables and call built-in functions. Probes are grouped by provider. Commonly available providers include DTrace for begin and end probes, profile for profile and tick probes, and syscall for system call entry and return probes. Appendix C lists all of these. Wildcards can be used in probe fields. Specifying that a field only contains a wildcard is the same thing as leaving the field blank. Lastly, the colons in these combinations are name combinations are equivalent. Try listing all of the read system calls, but include an asterisk after the read. The begin probe fires when scripts begin and can be used to initialize variables or print headers, and the end probe fires before the script exits. Profile allows one to profile the user specified rate, say 1234 Hertz, and 1234 can be changed to a different number. The fastest possible sampling rate is 4999 Hertz. Tick probes fire after n seconds. The probe in this case would fire every second. The syscall provider instruments the entry and return of system calls. This probe fires when the read system call begins, at which point the entry arguments can be expected. To print bytes requested using arg0, which is the third argument to the read system call. Return fires when the read system call completes. To trace only errors, use arg0 less than 0 and a predicate. And trace error now. You do not need to declare variables before using them. By default, integer variables are of type int, signed 32-bit, but you can cast a number to change its type. All of these are the number 1 as unsigned 64-bit integers. Use int and string respectively to cast integers and strings. DTrace supports 16, 32, and 64-bit signed and unsigned integers. U and L may be used instead of unsigned and long, respectively. Floating point types may be used for tracking and formatting with printf, but operators may not be applied. Strings may use the same operators as other types. Strings are null terminated, empty strings are equivalent to null. C arithmetic operators are supported for integers only and work the way you would expect. DTrace supports unary operators. Relational operators may be applied to integers, pointers, and strings. DTrace includes Boolean operators and bitwise operators and the ternary operator. See Appendix B, which lists LAs. Variables can store scalar values like this. Associative arrays store key value pairs, and keys may consist of multiple values separated by commas. C structures and pointer operations are supported. Structures can be added to D scripts explicitly, or the header file that defines them can be included using the TAC_C option. Many structures are already known to DTrace. For example, the current process info arrow PR_PSArgs is a built-in type of struct PSInfo. And in this example is only possible because in Solaris, the FBT provider knows that the first argument to fopcreate is a vnode, following the v_path member, which is what we want to retrieve. Thread local variables are stored with the current thread of execution and have the prefix self arrow. To declare a thread local variable, simply set a value. To free thread local variables, even strings, set them to 0. Unless explicitly freed, thread local variables aren't freed until the thread is destroyed, so free them to prevent memory from being consumed needlessly. Clause local variables are for use within a single clause. If there are multiple probes, clause variables do not need to be freed. If there are multiple probe clause groups for the same probe, clause local variables can be accessed across clauses. There are a number of built-in variables, always available for use in our scripts. arg0 through 9 allows us to access the probe's arguments. When a probe has a name of entry, these often allow us to inspect the arguments of the kernel functions, just like running a debugger. In this case, arg0 would be a pointer to file descriptor, arg1 to buff, and arg2 to count. For return probes, arg0 would let us know how much data was read or written. The args array doesn't nearly the same thing, but is aware of types. For example, assuming the argument we're interested in is a pointer to a struct, and if we wanted to access a member of that struct, we must use the args array, which may understand the argument's type. CPU provides the CPU ID for the current CPU. Current PSInfo shows the current process state info for the current thread. CurThread is the OS internal kernel thread structure for the current thread. Errno, the error value from the last system call. Exec name, the name of the current process. And PID is process ID. PPID is the parent process ID. Probe_prov is the provider name of the current probe. Probe_mob for module. Probe_func for function. And probe name for the probe name. Stack depth, the current thread's stack frame depth. TID for thread ID. Timestamp, nanoseconds since boot. UID, the current process's real user ID. uregs array, the current thread's saved user mode registered values. vtimestamp, current thread's on CPU time in nanoseconds. While timestamp, nanoseconds since epoch. It's common to use variables and predicates to gather data for specific purposes, for processes, threads, and applications. DTrace also has what are called macro variables. $target is the same process ID passed to DTrace via TAC-P, or it's the derived process ID when executing a command via TAC-C. Use $1 through $n to retrieve args passed to DTrace from the command line, or $1 through $n, which gives you the same, but the types are coarse to strings. These can be used in aggregates like this to limit by process ID. Pass the command line using DTrace TAC-D. Use backticks to get access to variables defined by the operating system. There's only one example in the book on page 231, but we're not going to cover it in this video. Aggregations are special value variables used to summarize data. They are prefixed with an @ sign. This is not the same thing as incrementing a global scalar, because that approach can suffer data corruption from simultaneous writing across CPUs, as well as a performance penalty for accessing the same location. Aggregations avoid this by populating data in per CPU buffers, which are combined when printing. They cannot be tested in predicates. Aggregations may have one or more keys like associative arrays. They can also contain certain functions or actions, like those that print kernel and user stack traces. Use these functions with aggregations. Count to get the number of times called. The others do what you'd expect. Sum for totals, average, min, max, standard deviation, L-quantize, which is a linear frequency distribution, and quantize, which is a power of 2 frequency distribution, with buckets like 0, 2, 4, 8, 16, 32, 64, and so on. There are 4 additional functions to manipulate aggregations. Trunc can either completely clear an aggregation or truncate an aggregation to the top number of keys specified. Clear clears values but leaves the keys. Normalize divides the aggregation by a value. Use this to convert from one unit to another. Print A allows one to specify the types for both the keys and the values. It's possible to change the sort behavior using agsort key, agsort reverse, agsort, and agsort key POS. Trace prints a single argument using a type-appropriate method. TraceMem does something similar for regions of memory starting with the pointer passed. Because DTrace operates in the kernel address space, copy-in is required to access the userland address space associated with the process. For example, the buffer pointers on the read and write system calls are example of userland pointers that require the use of copy-in. DTrace has printf like in C. Your format string will have as many % letter combinations as you have additional numeric or string arguments. In the purple comment, you can see the output of a simple printf example. And there are some additional formatting options. Use a number in between % and the format directive to specify a width. Compare the two comments. 10 and 200 have been padded with spaces. 40,000, which has 5 digits, simply overflows. Use a - sign to change the justification. When the width is specified, one can also add a length to specify the number of digits to zero fill. Use stringf to let printf know a pointer in kernel address space is a string. Use copy and string to print userland pointers. Stringlen and string join do just what they say. By itself, stack prints a kernel stack trace and backtrace. With a whole number argument, stack limits to the number of stack frames displayed. Stack can be used in aggregations. In this case, a count would be displayed for the number of times DTrace saw this path executed. uStack fetches the current user stack backtrace. Stack store addresses of functions, and only when printed are the addresses translated into symbols. If a process is terminated before DTrace prints a stack trace for it, the addresses will be displayed in hexadecimal. JStack is like uStack, but may insert native language stack frames. Size of works just like size of in C. To exit DTrace with success, use exit 0. Speculations provide a way to tentatively trace data and then later decide whether to commit it, print it out, or discard it. To print into a speculative buffer, use put speculate before printf. Commit will commit the speculation, printing all the contents of the speculative buffer. Use discard to discard the speculation. Translators are special functions that convert one data type into another. This example takes the variable and applies the appropriate info t to retrieve the name member. If we were of type _impl_t, the following translator would be used to provide access to the name member. Place custom translators in /users/lib/dtrace. Appendix B lists all the available functions. DTrace can also perform some destructive operations when TAC-W option is set. Use TAC-H to list the available help options. Use TAC-C to run a command when you start DTrace. TAC-N to specify a probe. TAC-O to append output to a file. TAC-P to attach DTrace to a process and exit when the process exits. TAC-Q suppresses the default output. TAC-S to execute a script. TAC-W to allow destructive operations. And TAC-X to set an option. Options can be set in scripts using pragma. Instead of using TAC-Q on the command line, we're using the quiet pragma option. To decrease the latency for traced output, increase the switch rate from the default of 1 Hz to 10 Hz. Many options can be set on the command line. Flow indents on every function entry and unindents on function returns. Keep this option in mind. For the complete list, see Appendix D. Let's play around with the begin and end probes in the DTrace provider. Begin fires when the script starts, and end fires before the script exits. After pressing enter, the script starts and the begin probe fires and we see hello. After pressing Ctrl-C, the end probe fires and we see world. The probe fires every time we enter the open system call. When an open happens, we print the application name and path. We know arg0 is the path because we look up the open system call's arguments in its man page. Let's run the script. We see the default probe output, the name of the application, and the path the process wants to open. Fork and exec are fundamental to process creation. We can trace these system calls. Here's our one-liner. We glob fork to get both entry and return probes. And when they fire, we print process ID. We see the default probe output along with the process ID responsible for entering or returning them from fork. Let's do the same for exec, but instead of printing on the PID, we'll use the executable's name. And we get similar output. Note we globbed for exec, and if we hadn't, we wouldn't have matched the probe we're interested in, exec VE. Here, an aggregation is used to count system calls from Mozilla Firefox. In this case, Firefox called psync_ch_cv wait over 55,000 times. We can see the actual number of bytes read. Quantize produces a power of 2 frequency distribution by process name. You can see I've truncated the output to only display VirtualBox and terminal. VirtualBox shows a unimodal distribution, and terminal shows a quartile distribution. If you see negative values in histograms, those represent errors. Although there are exceptions like fork, function calls typically return from the same thread that they enter, so a thread local variable can be used to associate events. When we enter the write system call, we set a timestamp to a thread local variable using self arrow s. Then when the write system call returns, we see if the thread local variable s has a non-zero value. When it does, we take the difference between now and when the time saved in s. Remember, thread local variables need to be freed by setting their values to 0. Here's a distribution that shows in nanoseconds how long writes took across all processes. Let's do some profiling next. At a rate of 997 Hz, we're going to count by application name the number of times an application called any function. After 1 second, we print the results and then clear the aggregation so that we can repeat the process. Here we see PowerPoint didn't do much, but relatively kernel_task did. Also note DTraces in these results. Next, let's look at a script to look at executing processes. Quiet means to only print explicitly traced data. Increase the default switch rate to decrease output latency. The printf format in the begin probe for headers. Match the formats used to print the data. Lastly, we're using built-in DTrace variables to get the time since the epoch, the user parent process and process IDs, as well as the name of the current process. Okay, in summary, in this chapter we summarize the D language, including the syntax, operators, and built-in functions. You can find full reference tables for these in Appendixes A and B. The remaining chapters continue to demonstrate D as used in one-liners and scripts. Okay, starting part 2. Chapter 3 is the system view, and this will give us a good overview of using DTrace to solve problems. So DTrace is really about solving problems and understanding workload behavior. Some problems can be quickly correlated to a specific area of hardware or software, but others have a potentially broader source of root causes. These require starting with a system-wide view on using non-DTrace-based tools that make a first pass, and then complement them by using DTrace to take analysis further. Specific hardware subsystems, networking, disk I/O, file system, and specific applications are covered in greater detail in later chapters. So what do we mean by system and system view? We're referring to a coarse decomposition of the various components that make up your computer system, like the following. Processors, including multi-core CPUs, memory, disk I/O, and network I/O. Since DTrace can instrument the entire system, finding a starting point can be daunting. But first, use the same step. Define the problem in terms of something that can be measured. Performance examples include measuring the response time and the time to batch jobs. Time can be measured. A system view starts with bundled tools to get an idea of how the system is performing. For an in-depth performance coverage, see Solaris Performance and Tools, as well as Systems Performance Enterprise in the Cloud. System Methodology Guidelines. How busy are the CPUs? Is there idle time? Are CPU cycles being consumed in user mode or in the kernel? Is CPU utilization relatively flat, or does it fluctuate? What code paths are making the CPUs busy? Are interrupts consuming CPU cycles? Are the CPU cycles spent executing code or stalled on bus I/O? Is the dispatcher run queue consistently non-zero? Does the dispatcher run queue depth fluctuate with bursts of runnable threads? Focusing on memory now, does the system have sufficient memory? Is the system swapping or paging due to memory pressure? Is the page scanner running? How much memory are processes consuming? Does the system make use of shared memory? How much time are applications spending allocating and freeing memory? How much time are applications waiting for memory pages to be paged in? Is there a file system component to the workload where the file system page cache needs to be factored in as a potentially significant memory consumer? CPU checklist. Utilization, high %sys. The system is spending what appears to be an inordinate amount of time in the kernel. This may or may not be a problem. Some workloads are kernel intensive, for example NFS file servers, network intensive workloads, and so on. A kernel profile is the first step to determine where in the kernel CPU cycles are being consumed. Utilization, high % user. When burning CPU cycles, for most applications, it's generally good to be spending most of the time in user mode. But that leaves the question of whether cycles are being spent getting real work done or potentially spinning on user locks or some other area of code that's not advancing the workload. A profile of where the threads are spending time can answer this question. Wait time. Are threads waiting for an available CPU? This is known as run queue latency and is easily tracked in Solaris with prstat capital LM monitoring the lat column. DTrace can be used to measure how much time threads are spending in run queues waiting to run. vmstat TAC-R column shows the system-wide runnable threads. Configuration. Solaris provides resource management tools such as processor sets, resource pools, CPU management, and different scheduling classes and priority control mechanisms that can affect CPU usage. Interrupt load. Modern I/O devices, especially 10 gigabit network cards, can generate a high level of interrupts to CPUs. If application threads are sharing those CPUs, they may be getting pinned frequently by the interrupt threads, throttling throughput. It is sometimes advantageous to fence off interrupts, that is, isolate CPUs handling interrupts from CPUs running workload threads. Providers for tracking CPU usage. Profile and tick. These providers allow for time-based data collection and are very useful for kernel and user CPU profiling. Depending on how you say schedule, sched, or shed provider, observing scheduling activity is key to understanding CPU usage on loaded systems. The proc provider lets you observe key process thread events. sysinfo, this is important to tracking system-wide events that relate to CPU usage. FBT, the PIT provider, enables instrumenting unmodified user code for drilling down on application profiling. Lockstat is both a DTrace consumer, i.e. the program Lockstat, and a special provider used for observing kernel locks and kernel profiling. Observing system calls is generally a good place to start because system calls are where applications meet the kernel, and they can provide insight as to what the workload is doing. plockstat. This provides statistics on user locks. It can identify lock contention in application code. What processes are on CPU? Profiling at 997 Hz will count every function called by process ID and name. Which processes are on CPU running user code? When profile's arg1 variable is not 0, we're on CPU in user space. Here we're using arg1 as a predicate. Otherwise, this function is the same as the first. What are the top user functions running on CPU? We're going to use arg1 again, but this time we'll get the user function name from the probe context by using ufunc. What are the top kernel functions running on CPU? Profile's arg0 variable lets us know the kernel is on CPU. Func gives us the kernel function from probe context. What are the top 5 kernel stack traces on CPU and why? We use stack to get kernel stack traces, and we can use it as a key in aggregations. But before the script ends, we'll use trunc to limit the number of keys in the aggregation to the top 5. What threads are on CPU, counted by their thread name in FreeBSD? We'll get the thread's name by pulling the td_name member out of the built-in curthread variable. We then use string of to let DTrace know that the pointer that td_name points to is a string. Which processes are getting placed on CPU, event-based? We simply use shed on CPU, the rest we've already seen. Which processes are getting charged with CPU time when tick accounting is performed? First, what's PR_f name? We'll go to source.illumos.org. We select Illumos Gate from the In Projects area and type pr_name into the symbol field. And in procfs.h, it seems it's the name of the file that we're executing. We can infer that PR is process and fname is file name. Next, let's sample processes at 997 Hz that are on CPU in user mode and store results by process ID and process name. Avoid rates of 1000 Hz and 100 Hz to avoid sampling in lockstep with regular events, such as kernel clock interrupt, which happens every 10 milliseconds. The profile probe has two arguments. arg0 is the program counter of the current instruction when the CPU is running in the kernel. arg1 is the program counter of the current instruction when the CPU is executing in user mode. Thus, a predicate of arg0 or arg0 not equal to 0 means is the CPU running in the kernel. And a predicate of arg1 or arg1 not equal to 0 equates to is the CPU executing in user mode. Let's say the previous script, which sampled processes running on CPU in user space, resulted in this output. Showing counts by process ID and process name. We see process 2674 showing up most frequently. Let's look at PS and see if that makes sense. It's typical to see Oracle's log writer have several busy threads. Keep this as Oracle example in the back of your mind as our next examples will build upon it. Next, let's continue our understanding of this workload by looking at CPU usage in more detail to see where the kernel is spending time. This script is executable. We're profiling at 997 Hz. We'll look at this predicate in a moment. Remember, arg0 is kernel on CPU. We're counting kernel stack traces. After 10 seconds, we limit our output to the top 10 stack traces. We print our results and then exit. In Solaris, the idle loop priority will be set to -1 during execution. Verify the suggestions in the next table work for macOS X and FreeBSD. There have been changes in your operating system more than likely. To filter out the idle thread in Solaris, use curthread arrow t_pri not equal to -1, as we just saw in the previous script. Profiling refers to the process of determining what area of code a piece of software is spending its time. See the hot kernel and hot user scripts in the DTrace toolkit, which post-processes DTrace output to provide percentages. A line in a kernel stack frame is made from 3 parts: the name of the kernel function prefixed with a backtick, and then ends with the offset into the function in hexadecimal derived from the program counter. User stack traces have a similar format. Kernel profiling. This script can be executed directly. Default output is suppressed. We'll sample at 997 Hz. This clause only executes when the kernel is on CPU and not in idle. Looking at our clause, colors the program counter location of the current thread just before entering the current probe. Func gives us the symbolic name of the kernel function that caller points to. arg0 is the kernel function on CPU. Again, func gives us the symbolic name for the pointer arg0 points to. After 10 seconds, we truncate output to the top 20, and then print our results and exit. Let's run it. The output shows the top kernel function is mutex_enter, followed by disp_getWork, and so on. Let's dig into mutex_enter. So we've run our probe here. Looks like we've got a problem. Mutex_enter probe that we want doesn't seem to exist. Let's list our probes. And we'll use grep rather than find, mutex underscore enter, to find a probe. Instead of using the FBT provider, we'll use mutex underscore enter from the lock stat provider. This stack trace happened almost 2 million times. This stack trace shows the write system call being called. Continuing up the stack, we see sockfs is responsible for the write. The other stack trace, which is not shown here, shows almost exactly as many reads. Let's see if we can find the source of these system calls. Let's build this up. We know we want to count reads and writes, but how do we limit to sockfs? Let's pull up the man pages for read and write and see if there's something we can use. This first argument for file descriptors looks interesting. Let's look up some of the built-in variables again. In this case, arg0 would give us the file descriptor, and the FDS array can translate it. Okay, let's add these in. We'll start by adding arg0, and then we'll use the FDS array to convert the integer to a file underscore t struct. We'll then access the file system type via fi underscore fs member and only execute our clause when the member equals sockfs. Next, let's add exec name to see the process names. And because multiple processes can have the same name, let's add PID as well. Okay, let's run this script. The resulting output shows that our Oracle workload processes are generating the network IOs, which accounts for why we see kernel spending most of its time in network mode. Next, let's see how many bytes we're sending over the network. Our step is the same as before. arg2 probably has the number of bytes, and it does, but remember this is the number of bytes requested, not the number of bytes returned. And finally, every second we're going to print the results and clear our aggregation so that we can get data for the next second. Let's run our script, and every second we see results. Now let's get to the actual number of bytes read or written. So here we're setting a flag for when we enter the system call, and it's tested in the predicate for the return probe. arg0 is the number of, in the return probe is the value returned by the system call. And if there's an error, we'd get -1. The predicate filters out the error state so that -1 is not added to the sum by accident. Okay, validate read-write system calls are I/O related. Consult the man page on system calls to concern arg0 is returned as expected. Okay, FBT manages a great number of probes, so enabling a large number of them on a busy system, spending time in the kernel, will potentially have a noticeable probe effect. Here we execute our clause. Every time we enter a kernel function, when we start the script, we match 29,000 probes. This shows Unix and Gen Unix have the most activity, and as IP is the third busiest, there's also considerable network activity too. We'll drill down further by honing in on the Gen Unix module and count function entries for Gen Unix probes by probe function. probe_func provides the kernel function names in the GenUnix kernel module. Let's drill into the top kernel module functions displayed syscall_mstate and mstate_aggregate_state. Now we're only looking at the syscall_mstate probe, and since it's a single probe, we're going to get kernel stack traces to see why syscall_mstate gets called. Here we gathered kernel stack frames when syscall_mstate was called, and we see it being called right out of the system call trap handler. So the calls from functions in the GenUnix module are managing a high rate of system calls, calling into the associated per thread microstate accounting or mstate code. First, we gather a kernel function call count for the Unix module. bitset_find_in_word is the most frequent. Let's follow this by gathering kernel stack frames on the entry point of the most frequent kernel function. bitset_find_in_word. From the Unix module, we can see the stack frame that bitset_find_in_word is originating from a high volume of write calls. Let's bring in the missing stack frames. So once again, write system calls, 2 network sockets, and TCP. And ultimately the kernel is issuing a wake up 2 threads, 2 sleeping threads. Before moving on, we should point out that the use of FBT provider is an advanced use of DTrace. Proper interpretation of the data requires knowledge of the kernel, and you may need to examine kernel source code to understand what a particular function does. The FBT provider manages a lot of probes, so use it with care on busy systems, spending time in the kernel and potentially enabling a large number of probes via FTP. Kernel profiling applies, of course, when CPUs are spending enough time in the kernel to warrant having a look. If your system CPU utilization shows most CPU cycles are in user mode, it's useful to determine what is running and profile the user processes. Recall that the CPU utilization for this example indicated about 60% of CPU time is spent in user mode. What column seems to jibe with 60%? Let's validate with PRStat as well. PRStat provides another view of an Oracle workload, and PRStat shows us which processes have more than one thread. The number value following the slash in the last column. We see process 2674 has 19 threads. We can use PRStat to look closer. We just saw process 2674 has 19 threads. Let's look at them. We'll use PRStat, TAC-C, capital L, MP, and then the process ID. We ask PRStat to display the percentage of time the individual threads are spending in each microstate. Let's take a look at the user component of CPU utilization by using several methods. Let's look at processes getting on CPU. Again, the top process is the Oracle log writer, PID 2674. The largest count item is shed, which is the Solaris kernel. MacOS X uses kernel_task. Let's look at when the Solaris kernel is on CPU. There's not much of interest here. We're in the kernel idle loop for the most part. Let's look at the user mode component of the load. Let's get syscall counts for our Oracle log writer process. Here we see the time system call is the most frequently executed, followed by read, then write, and semsys, all typical for an Oracle workload. A simple change to the predicate. And let's see. Yeah, so a simple change, and instead of getting The Oracle one, we can do the same for a process that appeared earlier, and that's read, write, do it. Here again, we see our read, write, do it process is all about read and write system calls. What types of files are being read and written by these processes? Note we're using arg0 and the FDS array to get access to the fi_fs member again. Once again, it's sockfs. Getting back to the Oracle original process, it's useful to obtain user stack traces leading up to the frequently called system calls. We use the time syscall probe and use stack action. This is similar to the kernel stack trace. We've got external module, called function, and the offset into the function. The previous example truncated the aggregation to just the top 2 user stack frames. This is generally a good idea on a large, busy system running enterprise workloads because the sheer number of processes and unique stack frames can be extremely large. The stack frames represent the call path through the user code. The function names may not provide insight as to what the code is doing leading up to the execution of the system call. It is useful to examine the workload process that is the top CPU consumer. Recall in our previous example, the Oracle log writer process is our top CPU user. 16% of time was spent running on CPU in user mode, and 9% of the time was spent on CPU in kernel mode. arg1 is user mode, and ufunc and arg1 get us the user called function. KC RFW redo write is the most frequent. We think this makes sense for the Oracle log writer process. How much time is spent on CPU? We save a timestamp to a thread local variable, and when we get on CPU, and when we get off CPU, we calculate the difference. Thread local vars need to be freed. This script exits after 10 seconds. 200 microseconds over a 10-second period isn't that much. These threads aren't that CPU bound. Our thread's waiting for their turn on CPU. Using enqueue and dequeue, we do the same timing trick. PRStat tech C capital L M 1 is a great tool to do the same. Lat is run queue latency. Let's measure the actual time spent on the run queue. The plat.d script uses a predicate with the shed enqueue probe. That checks the PID of the processes enqueued with the $target DTrace macro, which is expanded to the PID passed on the command line when the script is executed. The sum function is used to track the total time spent between enqueue and dequeue every second. On average, our process is spending 110 milliseconds in each 1 second period waiting for CPU. Run queue depth refers to the number of runnable threads sitting on run queues waiting for their turn on CPU. Using the shed provider's enqueue and dequeue probes, we increment an array variable, qlen, indexed by the CPU ID, and set a clause local variable, thisArrowLen, to that value. The aggregation on line 7 uses lquantize to provide a linear plot of per CPU run queue depth. The dequeue probe is used to decrement the depth variable when a thread is dequeued. Observing interrupt activity can be important in understanding and maximizing performance. Modern I/O devices such as 10 gigabit NIC cards and multi-port 2, 4, 8 gigabit fiber channel HBAs, SATA controllers, and so on can sustain very high rates of I/O, and interrupts are part of the system I/O processing. InterruptStat is a DTrace consumer included with Solaris, which provides more detail on per CPU interrupt load. On the left, CPU 5 is spending 51.1% of its available cycles processing E1000G interrupts. Let's investigate. CPU is a global variable, and using it in a predicate in this way enables profiling a specific CPU for groups. The kernel stack trace output captured when mutex enter is called validates that indeed mutex lock calls are coming up from the E1000G interrupt handler. This is reasonable given the system profile showing virtually all kernel cycles spent in the E1000 driver code. If the presence of the kernel mutex lock raises concerns using lockstat to see kernel lock contention, the lockstack data indicates that the top mutex spin events and mutex block events occurred in the E1000G driver routines. The mutex spin data on the first indicates a total of 19.3 milliseconds was spent spinning on a mutex during sampling period of 10 seconds. Various system events, notably MPStat and Solaris, provide statistics on key metrics for each CPU. When observing CPUs, it's often useful to further track the source of these statistics. This program enables every single probe managed by the sysinfo provider. Using the tick provider, our simple command provides per second statistics. Here we can see more than 300,000 PS switch events per second, followed by write tech and so on. We saw earlier examples of how to look deeper into context switch activity using the shed provider to determine which processes and threads are getting on CPU. We can also determine why threads are being switched off CPU by looking at user stack and kernel stacks when off fires. The kernel view aligns with what we see in the user stack trace. Threads are being switched off because kernel blocking on read and write system calls. In the kernel stack example, we also see instance of blocking on semaphore operations. And top kernel stack, we see blocking on pwrite system call used to a UFS file. These scripts are basically the same. One does user stack traces, the other does kernel stack traces. The kernel view aligns with what we see in the user stack trace. Threads are being switched off because blocking on read and write system calls. In the kernel stack example, we also see an instance of blocking on semaphore operations. And in the top kernel stack, we see blocking on a pwrite system call to a UFS file. We're looking at all reads and writes. Continuing with the previous example, reads and writes observed using the sysinfo provider can be better understood using the syscall provider. Reads and writes, no glob, and we're using the FDS array to get file system type. The vast majority of reads and writes are network sockfs, with a much smaller number of writes going to UFS reading/proc. Cross-calls are CPU to CPU interrupts. In Solaris, cross-calls are relatively lightweight events. Modern CPUs are capable of handling large volumes of cross-calls per second. Note sysinfo cross-calls. On the right, examining kernel stack frame starting at the bottom, we can see that most cross-calls originate from network writes, initiating a wake-up to sleeping threads. Let's apply the same approach to other system information, semaphore operations. Note sysinfo sema. Note semsys semop. Let's see what processes are entering semsys. Our favorite process, 2674, has the most. We'll do the same thing again, but limit to process ID 2674. And we see user code paths are the culprits that lead up to the semaphore call. Here again, 3 consecutive executions illustrate potential for rapid drill down. We can apply the same method for understanding the source of CPU statistics and events by grouping related events together with multiple probe specifications. In sysinfo, we're looking at both sysread and readch. Counting process by ID and probe name. This information shows us which processes issued the most read calls during the tracing period. The metrics of interest when observing CPUs are utilization and saturation to see whether CPUs are a contended resource. DTrace can determine which workload processes or threads are using CPUs, down to the software functions responsible in both user land and in the kernel. As in the case with all things performance, latency is a critical measurement, and CPU latency, both time waiting for a CPU and time running on a CPU, is measurable with DTrace, as shown in this section. Several utilities are available for monitoring memory system-wide, as well as per process virtual and physical memory. Which you should use depends on memory problems or capacity issue observed, or whether the goal is simply to account for memory use. With DTrace, we can do the following. Dynamically monitor kernel memory allocation and determine whether kernel subsystem is consuming memory. Dynamically monitor process memory allocation and determine where in user code memory allocation is originating. Correlate system-reported memory paging activity to application processes generating the observed events, page faults, page ins, page outs. Measure the memory-related latency in terms of how much the application processes are waiting for memory allocations, page faults, and other memory events. Depending on what the problem is and what's been observed, DTrace can be used to drill down on all aspects for memory allocation and use. When examining memory use, considering the main consumers of physical memory. The kernel, this includes executable code, I/O buffers, and system metadata. File system caches, these are technically part of the kernel, but a potentially large enough consumer to be treated separately. The file system being used, UFS, CFS, and so on, will determine the right method for measuring this. User processes, application code, and heap allocations. The first step in observing memory is to get a big picture view of how much memory is used by each of these consumers. Begin by using the operating system tool vmstat or on Mac vm_stat. This may be identified by checking how much free memory the system reports is available, if the page scanner is running, and if unwanted page in, page out activity is occurring. System performance degrades substantially if the kernel needs to continually locate pages for freeing and move active memory pages on and off the swap devices. Once system-wide memory is understood, further investigation can be done. Memory checklist. System-wide memory shortfall. The system does not have sufficient physical memory to support the workload, resulting in page in, page out activity. All operating systems generally perform very poorly when memory becomes a contended resource and there is sustained page in activity. Kernel memory allocation. Observed metrics indicate CPU cycles and memory consumption by the kernel. User processes memory allocation. Observed metrics indicate CPU cycles and user memory allocation, deallocation, and memory consumption. Memory page in, page out activity. Virtual memory statistics indicate memory page in, page out activity. Memory page fault activity. Virtual memory statistics indicate minor and/or major page fault activity. Major page faults require a disk I/O. Minor page faults do not. Memory providers. VMinfo, virtual memory statistics, syscall. Process memory allocation system calls like break, mmap. I/O. Observed disk I/O due to paging or swapping. FBT, kernel functions related to memory allocation, deallocation, virtual memory, and page management. PID, user process memory usage, trace malloc, and so on. PLockStat, user process locks related to memory routines. Memory one-liners. Track memory page faults by process name. Track pages paged in by process name. Track pages paged out by process name. Under the shed provider, track process user stack sizes. Track which processes are growing their address space heap segment. FBT provider. Track which processes are growing their address space stack segment. Use TAC-PPID or TAC-CC, or TAC-C in the command to specify a process. Process memory allocation via malloc, counting the requested size. Process allocation via malloc, user stack trace and total requested size. User process allocation via malloc by Java stack trace and total requested size. Memory analysis begins with getting a system-wide view of key memory metrics. Of course, it's useful to know how much physical memory is installed on the system and how much swap space is configured. On Solaris systems, these first basic steps can be accomplished using the following. PRT-conf, swap TAC-L. Next, get a system-wide view of memory usage and how much memory is free. In Solaris, use MDB. The previous Solaris VM stat sample shows a system with substantial amount of free memory, 59 gigs. The SR column, page scan rate, is 0. The SR column values indicate the kernel had to nudge the page scanner to wake up and start finding memory pages to steal to replenish memory free list. The RSS column shows the physical memory usage of the process. Size is the virtual memory. Be aware of workloads that make use of shared memory because each process will show physical memory usage that includes shared memory. If we were to sum the RSS column for all processes, the resulting value would far exceed the amount of physical memory installed because most of that 38 gigabytes is shared memory segment that is part of each process's address space. Only one copy of those physical memory pages is actual resident in memory. Note that this applies to other types of shared memory as well. macOS X does not appear to implement the break system call, so the underlying mechanism used to allocate heap segments is not readily apparent. Let's use DTrace to see if we can figure out how macOS X implements malloc by examining workload. The workload was a simple program written in C that makes 8 malloc calls in a loop, starting with mallocing 100 megabytes, and then mallocing 100 kilobytes to each subsequent malloc. We'll use DTrace syscall provider to see which underlying system calls are used. We enable a probe on the entry point of all system calls when the PID of the process matches on CPU, and when the probe fires. The malloc message are generated by the program. These aren't generated by DTrace. The result shows 16 calls to madvise and 7 calls to mmap as memory-related system calls. Referencing the man pages, we know madvise is not used to allocate memory, but mmap most certainly is. So it seems mmap is used in macOS X to enter kernel for heap allocation. Let's verify this by just tracing mmap. We changed the DTrace script just to enable a probe at the mmap entry point. And we traced the second argument past mmap. The second argument is size. And we can test the size arguments past mmap. These match precisely what our test program passes to malloc, so we can conclude that macOS X creates user process heap segments using mmap. Let's verify macOS X creates user process heap using map_anon flag. We changed the DTrace program to use a printf statement in the action. And print the value of arg3 in hexadecimal. We know from man mmap that the fourth argument is flags. and flags are defined in /user/include/sys/mman.h header file as hex values. So printing them in hex makes it easier to find our answer. The DTrace output shows 0x1002 as the flag argument to mmap, and an examination of the header file shows that indeed 0x1000 means map anon flag is set. 0x0002 is something else. Let's drill down further with DTrace and determine which OS X kernel function is being called. The mmap.d script enables all FBT provider probes. When mmap is entered, we set a flag that is used as a predicate in the FBT probes. Since an action is not specified, we'll get the default output of the CPU and the probe functions when FBT fires. Using the flow indent DTrace option, we'll generate an easy-to-read kernel function call flow. The call flow generated enables us to observe key kernel functions called for memory allocations. vmmap enter and zalloc. The zalloc function sounds interesting. Allocate zeroed memory pages is our guess, and can be instrumented to track memory allocations by processes. However, since we're not certain under what circumstances the macOS X zalloc kernel function may be called, we can stick with using a DTrace probe on mmap. Let's see the number of times processes by name are calling mmap and how much memory they are requesting. Let's pull up the man page. arg3 seems to be a flag. arg1 decides to allocate. The DTrace program here uses a predicate to determine whether the map anon flag is set, since our interest here is tracking mmap calls for heap memory allocation versus the use of mmap for requesting regular files. We also see that the 0x0002, which is map private, further reducing our output to only those allocations for private anonymous memory segments. During the sample period, we can see macOS X Windows Server process did 21 mmap calls for 16 kilobyte chunks of memory. In Solaris, the break system call is typically invoked when a user calls malloc, which is a user library function. So we can begin there to see which processes are doing memory allocations. It is important to note here that there are many memory allocators available for Solaris, implemented as binary compatible malloc calls in different shared object libraries. libc, libmtmalloc, libumem, and so on. These can be linked to your Solaris code to use different mallocs. Now let's trace the break memory allocation in Solaris. The output shows several Java processes doing memory allocations. The break system call in Solaris does not take a size argument, so we cannot easily determine the amount of memory requested in Solaris by using a probe on break. However, it is possible to track heap growth by doing some math on addresses passed to break, tracked over multiple calls. The break system call takes a memory address as the only argument, arg0. The predicate for the first action clause verifies the PID specified on the command line, and tests that the thread local variable self_ends is 0, in which case self_end is set to arg0. Another approach is to track size from a different level in the software stack. Specifically, we can instrument malloc library call in processes of our choice, but doing so requires the use of the PID provider since malloc is a library interface and resides in user memory, not in the kernel. The Java process we tracked here, PID 11089, did just a few malloc calls for relatively small amounts of memory. We could take this one step further and examine the call stack. Note the use of JStack. Note also that stack frames have been partially resolved. That is, some of the entries show hex numbers, user virtual memory addresses, and not symbol names. DTrace collects and stores stack frames in their raw numeric form and converts addresses to symbols only when it's time to display output, In some cases, DTrace may not be able to convert a user address to its corresponding symbol. This can happen if the process exits during tracing or the symbolic information has been stripped. Monitoring memory allocation in macOS X. In the previous example, we determined the PID of Firefox on macOS X. And we tracked malloc, requested sizes using quantize, along with aggregating on the user stack trace. With this running, we did a couple of web page loads with Firefox. The sample frame shows a larger number of malloc calls, i.e. the count values. Most are in the 8 kilobyte to 64 kilobyte range. Also of interest when monitoring memory is tracking kernel virtual memory events to the processes that are generating or waiting for those events. The DTrace VM info provider makes it relatively simple to correlate virtual memory events, processes, and quantify the effects on performance. On Solaris, we get the big picture with VMstat. These next two scripts, it's out of time. These next two scripts enable every probe managed by the VM info provider and aggregates on exec name, probe func, and probe name as keys. We use a printf statement to label columns, and we manage column width and alignment in the printf and print statements in order to produce readable output. The script is nearly the same as its predecessor, but it limits its output to the top 10 values. Since we're aggregating on process name, exec name, all processes with the same name, for example Oracle, show up as one line for a given probe function probe name pair. A predicate can be added to the vm.d script to just take action for Oracle processes. Exec name equals Oracle. An exec name could be replaced with PID as an aggregation key. Page-ins are interesting because they represent disk I/O read and are thus heavier weight operations than many other VM functions. Let's look at an example of drilling down on the M2 loader to get an idea of the page-in activity. This example shows an interesting approach, combining both the stack, the kernel stack, and user stack, DTrace functions as aggregation keys. It allows us to see the code path from the user process up through the kernel. Here we see M2 loader ultimately causes a page fault due to kernel functions and NFS4 get a page. Okay, so here's an example of using several functions to measure the NFS4 get a page time. We grab a timestamp at the function entry, and then when we return, we track the minimum, maximum, and average times along with the quantized plot to break them down. We also track a number of calls during the sampling interval in the entry probe. Note that the nfs.d script adjusts the min, max, and average times to microseconds, whereas the left column of the quantize aggregation function is in nanoseconds. We can see from the quantize distribution that most of the get a page operations are in the 1 microsecond to 4 microsecond range, with some outliers in the 16 microsecond. The 32 millisecond range, which aligns with the max value of 21.4 milliseconds. Interesting to note with this data is that the average value of 42 microseconds, which falls around the middle of the values in the quantized graph. Note that because the two modes, average is misleading. One of the key points to take away from this example is the method applied to determine what can be measured. By starting with some basic information, basic event monitoring, and drilling down with stack traces, we can see which functions are interesting to measure to understand the latency component of these operations. In Solaris, the VM's page-in, page-out facilities are invoked for most file system read-write operations. They are not just a sign of paging due to low memory. The pf.d script uses the FBT provider to instrument the kernel page fault function. All Oracle processes combined spent 1.45 seconds, and Java processes spent 5.7 seconds. Drilling into the underlying cause of page faults is more challenging. A page fault occurs when a process thread references a virtual address in its address space that does not have a corresponding physical address, an actual mapping to a physical memory page that does not exist. The page may be in memory, in which case the kernel only needs to set up the mapping, which is a minor fault, or the page may not be in memory at all, requiring physical disk I/O, major page fault. In a modern operating system, memory is demand paged, so the occurrence of page faults is not necessarily indicative of a problem. In Solaris, the kernel grow function is used to allocate space for stack growth. The two examples show the use of the same probe, but aggregating on different data. First, we aggregate on process name, exec name. We capture kernel stack frames, and second, which can be useful in understanding the underlying source of events, most of the grow calls originated as the result of a system trap, which is not at all unusual. The page fault trap handler will call grow to increase a stack segment. Tracing kernel memory is generally a complex process for several reasons. Solaris, MacOS X, and FreeBSD all implement sophisticated kernel memory allocation subsystems that leverage object caching mechanisms and reuse. The tools are available for observing kernel memory are cryptic in nature and require some knowledge of the kernel internals of the allocation mechanisms in order to use them effectively. The DTrace provider required to track kernel memory allocations is FBT, which, as we have pointed out several times, is an unstable provider. Using the FBT provider with DTrace to track kernel memory requires knowledge of the internals of the kernel and kernel memory allocation subsystem. Consult a book or other documents that document your operating system's internals as needed. In addition to DTrace, Solaris offers several tools for observing kernel memory. The mdbmemstat command shown previously, the mdbkmastat dcmd command, the kstat command. Given that the most frequently used cache in this example was a generic kmem-alloc 4096 cache, we can use a predicate and a kernel stack trace to determine which facilities are generating these allocations. The kernel stack frames captured for kmem-alloc from the kmem-alloc 4096 cache indicate most of these allocation requests are the direct use of page faults, or the direct result of page faults generated by user processes. Monitoring kernel object allocations continued. Recall that we can instrument page faults. Note the calls to kmem-alloc family of routines on Solaris do not necessarily mean physical memory is being allocated. Most of the time, the kernel is taking advantage of the design features of the slab allocator and simply reusing memory from its object caches. I'm not sure what these args do, so let's look these up. Recall tac lvn and the probe gives us verbose info about a probe. And on Illumos, we get argument types. arg1 looks like it's the requested size. arg0 is of type vmem. Let's look that up. Here I've looked up vmem on source.illumos.org. vmem_name is the area's name. And in vmem.h, the vmem_t type is defined to be a vmem of the struct vmem. The Solaris kernel implements a vmem layer as a universal backing store for the kmem caches and general-purpose kernel resource allocation. We see the largest kmem areas during the sampling period are kmem IO4G and kmem IO4. As before, we can use these names and predicates to capture kernel stack frames of interest. The previous example, monitoring vmem heap area, we can see allocation requests coming from the ZFS layer on behalf of read system calls and SATA driver for DMA operations. The seg kmem layer is the segment driver for kernel address space segments that gets called from the vmem layer. The following series of DTrace programs show a very similar flow to what we have used to look at for the kmem and vmem layers. We start with kmem. We see seg kmem xalloc, which certainly looks like an allocation function. And next we instrument the entry point to that function. Aggregating on the name of vmem area and calling into it the size. Finally, we take the name of the generated output heap and use it in a predicate in the third program, which captures this kernel stack. We can see seg kmem xalloc getting called out of vmem alloc, entered from the SATA drive for DMA memory. Kernel memory alloc is commonly but not exclusively used in macOS X kernel for kernel memory allocation. Instrument using the FBT provider and kernel stack traces to determine which kernel subsystem is allocating memory. The DTrace command used for macOS X instruments is entry point kernel memory allocate and aggregates on the kernel stack using quantize to track size allocation, arg2. We see several allocations in the 8 kilobyte to 64 kilobyte range, top stack, and from the trap code. Most likely page fault traps calling into the page encode. The bottom frame and associated aggregation shows 10 allocations in the 8 kilobyte to 16 kilobyte range, and 5 in the 64 kilobyte to 128 kilobyte range, originating from ioctl system calls. FreeBSD also makes use of a kmem layer for object caching kernel objects in kernel memory. When exploring a subsystem we're not familiar with, we often choose to look at which function of interests are getting called, in this case from the kernel kmem functions. We can instrument a function of interest, kmem_malloc, aggregating on kernel stacks. With the FreeBSD system shown here, we see kernel memory allocations coming up from lstat system calls through the file system layers into the FreeBSD kernel slab routines. Refer to Chapter 12 for more example of kernel DTrace analysis. Memory. When observing memory, the metrics that interest are used memory versus free memory, where used memory is being used, system utilities that provide system-wide metrics and per-process metrics on memory are the right place to start. DTrace can determine where and why the kernel and applications are consuming memory and measure the latency impact of memory-related events, such as page faults. Observing disk and network I/O. Once an overall view of the system can be established, use DTrace as your connect the dots technology to do the following. Determine which processes and threads are generating disk and network I/O. Determine the rate and latency of I/O to disks in the network. Determine the I/O latency profile of your application processes. Trace disk I/O targets, files, file system, raw devices. Device I/O profile. Which devices are target for I/O and what is the read-write breakdown? Device I/O latency. How fast are I/Os being processed on a per-device basis? All right, well, I guess that's the end. Okay, I don't know which page we were on. Okay, and we're back. So let's see. Device I/O errors. What device errors are occurring, and are they being handled by the OS? Application I/O profile. Which components of the workload are generating I/O? Application I/O latency. What is the cost of I/O latency in terms of delivered application performance? Application I/O error. Is the application encountering I/O errors? What provider should we use for I/O? I/O, stable provider for observing physical disk I/O and NFS backend I/O on Solaris. Kernel in our I/O flow diagram. FBT kernel memory modules and functions related to disk and network I/O. In our I/O diagram, system calls flow through the device driver. Syscall, application issued system calls for disk and network I/O. MIB, message information based provider, traces counters served by SNMP. Socket network I/O in our diagram. IP, stable provider for observing IP layer network traffic, also network I/O through sockets in our diagram. FSinfo, file system operations in Solaris, file system on our diagram. VFS, virtual file system provider on FreeBSD. Going through our I/O diagram, for threads running in user mode and library API calls, use PID, profile, tick, and shed providers. For system calls, use syscall and FBT. For kernel, use FBT, profile, tick, and I/O. For file system I/O, use FSIO, FSinfo, and FBT. For network I/O through sockets, use FBT, IP, TCP, UDP, and MIB providers. And finally, for device drivers, use FBT and SDT. These may need adjustment to match the system calls on your operating system. For example, syscall glob read entry does not match the read no cancel system call on MacOS X. Which processes are executing common I/O system calls? Which file system types are targeted for reads and writes? Which files are being read and by which processes? Which files are being written by which process? Which processes are generating network I/O on Solaris? Which processes are generating file system I/O? What is the rate of disk I/O being used? When observing I/O, it is important to be aware of the synchronous nature of I/O and how this affects what typically happens when a thread issues a read or write to disk, network interface, or file system. At some point after a system call is invoked, the calling thread will be put to sleep while the I/O moves down through the kernel, through the device driver, out over the wire, and back again. Once the I/O is completed, the kernel will copy the data to the thread that executed the read or write and issue a wake-up to the thread. As illustrated in Figure 3.2, once an application thread issues an I/O, it will be taken off the CPU until the I/O completes. The actual processing of the I/O through the kernel layers down into the device driver happens asynchronously with respect to the thread that issued it. From an observability perspective, this means that when you're instrumenting lower layers of the I/O stack and want to correlate I/O events, processes and threads using DTrace variables, exec name, PID, and thread ID, may not provide the expected results because the issuing thread will not likely be on CPU when the probes instrumenting the lower layers of the I/O stack fire. First, observe what processes are issuing I/O system calls. On Solaris, we see several processes executing reads. This enables the syscall provider probes for various read-write system calls. Using the glob pattern matching character in the probe func field, as noted previously, this may result in matches on system calls that are not of interest, like readlink on Solaris. So you should verify which system calls will be instrumented on your target host by running DTrace-ln and then the probe. and the same for the write probe. Here we get a better view of I/O target by observing which file system layer is being used, giving us more insight to the nature of I/O load on the system. Here we are looking at I/O in the system-independent layer of the kernel. Probe name enables us to observe the specific file system operation. We also use the file system type and the full path name to the file. Finally, we use trunc to display the top 10 events. We enhance our view with more detail using the fsinfo provider by taking advantage of available arguments. arg0 is a pointer to the file finfo structure, and args1 is a return value from the file system operation associated with the probe. A return value of 0 means success. Other return values depend on the actual file system operation. For example, the return for fop read and fop write is the number of bytes written. See file info_t. It may be easiest to start looking at disk I/O with bundled tools such as IOstat, which gives us a system-wide view showing key disk I/O statistics on a per device, per controller basis. Let's drill down. What processes are generating I/O? What system calls are Java processes using to do I/O? Let's drill into extensive pread64, prewrite64 system calls. Finally, let's just instrument those system calls. The previous drill down is good and useful information, but in order to properly characterize the load on the system and the application, we need to generate a few key performance metrics. I/O rate. What is the rate of reads and writes per second? I/O throughput. What is the data rate of reads and writes? I/O latency. How long are the disk reads and writes taking? We can see Java processes are doing about 6 kilobyte reads, just more than the 9 kilobyte write per second per disk, with about 48 megabytes second of read throughput and 77 megabytes per second of write throughput. With the I/O rate throughput numbers in hand, the remaining metrics of interest is latency, or how long disk IOs are taking. The /user/demo/DTrace directory on Solaris system includes a DTrace script, iotime.d, which will provide per I/O, per device I/O times. This script will generate a tremendous amount of output if there's a steady rate of disk I/O traffic and many disk devices handling I/O. We can modify the script to use an aggregation and grab a snapshot to track per device I/O times. The previous truncated sample output shows the quantize aggregation function. Reads on dev SSD 153 and writes on SSD 148. Most of the I/O time falls in the 8 millisecond to 31 millisecond range, and some writes are approaching 120 milliseconds, which is extremely slow. Invoking this script requires passing the name of the system call to be measured as the first command line argument, $1, line 7. And the process name is used in the entry probe predicate. You would typically run the script after having done system-wide system call profiling and determine which processes are generating I/O. The path names in this example have been truncated due to their length. We measured the time of write system calls for all processes named Java. It's easy to change the aggregating function from sum to average to get average time, or quantize to get a distribution. Chapters 4 and 5 cover I/O and file systems in depth. As with disk I/O, network I/O begins with system calls from applications. In addition to the system calls listed in the disk I/O section, applications performing network I/O may use getMessage, and put message, as well as any number of Section 3 socket interfaces, many of which are implemented as system calls. For example, receive, receive from, send, send to, and so on. For the most part, applications that perform network I/O use standard socket interfaces, which on Solaris systems are implemented via the sockfs file system. This makes connecting network I/O activity to processes and threads a snap. Here's a script that builds on the sockfs example in the one-liner section. Here, and in the script that follow, sock_j.d, we leverage the existence of the sockfs layer in Solaris to connect network calling processes. For macOS X and FreeBSD, which do not implement sockets with sockfs, the FBT provider can be used with a blank field for the probe mod and a wildcard character for the probe function field, using the entry probe name. This is a good start. Let's drill down. We start by limiting instrumentation to Java processes, which allows us to use PID as an aggregation key. The timestamp is saved in self_st stack depth, which associates not only the time the current thread, self_st, but also the time with the current level of the stack by using stack depth built-in variable. This is because the entry probe may fire multiple times as the sockfs subfunctions are called before the probe is fired. Using stack depth as a key associates each entry with the correct return, despite the subfunction calls. In the tick probe, we convert the times from nanoseconds to microseconds using the normalize function, and print every second. Time spent in network functions. This output shows the time spent by specific Java processes in network functions in the kernel. The PID 21.28.1 spent 638 milliseconds in the sock_tpi_read and 582 milliseconds in the so_tpi_receive message, and so on. Since these functions include subfunction calls, the times overlap. The function call with the highest time is likely to be the highest in the stack and include the others. Even though the function so_update attributes was called the most frequently, 13,000 times in the 1 second interval, the time spent in that code was relatively small, 17 to 20 milliseconds. This illustrates the importance of not just rates, but time as well. And latency matters for most applications. Find out where kernel socket functions are originating. In the previous script, we were interested in socket update attributes. We could see from the output that the socket update attributes kernel function, not in the stack trace even though it was the cause, gets caused when the application code reads and writes sockets. Let's use the file descriptor array FDS to track I/O system calls to the sockfs file system. Once again, with a few tweaks to the command, and we can drill down on a process of choice and measure the requested number of bytes. Here we track the MySQLD process, focusing on read bandwidth. With per second ranges showing a pretty wide spread, it may be more interesting to use quantize for a distribution of read sizes. Distribution of read sizes for MySQLD. Node exec name is MySQLD, and we're looking at network traffic via sockfs. We removed the tick probe and chose to sample for a few seconds before hitting Ctrl+C. This gives us a better view of the distribution of the size network reads for this process. We see most are very small, 4 to 8 bytes, with a large percentage in the 128 to 1024 byte range. As was the case with disk I/O, determining which processes are generating network I/O can be a good place to start, but it's also important to understand rates, throughput, and latency. We can use scripts like we did in the disk I/O section to obtain this information. Measuring the rate and amount of data requested. This script captures two aggregations using probefunc, read or write as the key. every second we get output, and this output indicates that we're doing substantially more reads than writes by a factor of about 3 to 1, and generating more read throughput than write throughput. If applications are using other APIs such as getMessage and putMessage to read and write network data, we would need to include those interfaces in our script. This is because getMessage and putMessage have a very different argument list than read and write, also the same with send and receive. And that concludes chapters 1 through 3. I hope this was beneficial to you. Good luck, and we'll see you soon.